In this section, we will talk about solving trigonometric equations. In a previous lesson, we took a look at an application of trigonometric functions where we had a population of a city that had risen and fallen over a 20-year interval. Its population was modeled by the function y equals 12,000 plus 8,000 times the sine of the quantity 0.628x, where the domain was the years since 1980 and the range was the population of the city. We used this model to then predict the population in the year 2010. Now, the solution first made us have to figure out what was the thing that we were solving for. So we were asked to find the predicted population, and we knew that the predicted population had to do with the range. So we knew that we were solving for y. Therefore, we must have an x. And in this case, we were talking about the year 2010. We determined that the year 2010 was 30 years after 1980. And the reason we used 1980 was because the domain was defined as the years since 1980. So, how many years has it been since 1980 that you're now in the year 2010? Well, that x value of 30 came about by taking the year 2010 and subtracting the 1980 year. Okay, so we got x equals 30. We then substituted that x equals 30 into the placeholder where we saw the x. And when we put that into our calculator, we got approximately 11,923.55. If we want to round to the nearest whole person, then that would round up to, in the year 2010, the predicted population would have been approximately 11,924 people. We then ask the question, well, what if we want to do the reverse? What if we want to predict the year in which a city has a certain population? So using that same example, the question is now, in what year will the population reach 18,000? So now we're substituting the value of 18,000 in as the output. In other words, that is the y value. So I wrote 18,000 equals 12,000 plus 8,000 times the sine of the quantity 0.628x, and tried to solve for x. My first step was to subtract 12,000 from each side and then divide by 8,000. That gave me on the left 0.75, and we set that equal to the sine of 0.628x. All right, now at that point in the previous video, we were a little stumped because we didn't know much about inverses, but now we do. So what I'm going to do next is I'm going to take the inverse sine of each side. So I'm going to take the inverse sine of each side. All right, and on the left, when I put that into my calculator, inverse sine of 0.75 gives me the decimal approximately 0.848. And on the right-hand side, the inverse and the sine undo each other. So I'm just left with 0.628x. Now, if I divide each side by 0.628, on the left and on the right, I got an x value of approximately 1.35. So we would say that the predicted population of 18,000 people, will occur about 1.35 years after 1980. All right, so here is that solution that we just calculated, just written out a little bit more formally. And we see at the top, there's a question. Is there only one solution to this application, or we might say to a trigonometric function? And the answer is no. And the answer is no because we know that there is a periodic nature to these trigonometric functions. Now, a graph might help us see that. So in this graph, we see a sine curve, which is the population model of y equals 12,000 plus 8,000 times the sine of 0.628x. Along with, now let's put the graph of y equals 18,000. 18,000 is coming from the population that we were interested in. And what we see in this intersection of these two graphs is that they are intersecting in 1, 2, 3, 4, 5, 6, lots of different places, right? 6 that we can see just on this image, but we know that to the left and to the right that those intersections will just continue indefinitely. Now, the answer that we got, the 1.35, that 1.35 is just the first solution. So the question is, how do we get those other values? We can see them, but how do we algebraically determine what those values are? If we go back to the unit circle, we may see the reason why or where those other solutions are coming from. When we algebraically solved this, on the left-hand side, we were trying to determine what angle would produce a sine of 0.75. Now, a sine of 0.75 occurs in either the first quadrant, where we see the height of about 0.75, or it also may occur in the second quadrant, where we see a height of 0.75. So there should be, at least in one rotation around a circle, both a quadrant 1 and a quadrant 2 solution. Now, when we put this into the calculator gave us just that quadrant 1 answer. Just gave us the quadrant 1 answer. And that's because of the limitation that we talked about on the inverse sine function. But again, we know that there's more than one solution. It's just in order to be a function, the calculator is producing just that one answer. So our job is to determine what is that quadrant 2 angle measure. So if I'm starting on the positive x-axis and I want to get all the way around to that quadrant 2 angle, what is that angle? That's what I want to determine. Well, in order for an angle to have a sine of 0.75, if there's more than one angle, what we know is that those angles must have the same reference angle. And a reference angle, as you might recall, is the positive angle measure that is between the terminal side of an angle and its closest x-axis. So for quadrant 1 answer, that reference angle would be this piece. We'll just sort of highlight that in, right? It's going to be that piece right there. For the quadrant 2 angle, remember it's the terminal side to the closest x-axis, that's going to be this piece. And I hope that you recognize that those two angle measures that I've just highlighted, that those are the same. Okay, if you have the sine of an angle equals 0.75, then whatever that angle measure is, those reference angles have to be the same. So that might help us a little bit, because here's what we know. We knew when we plugged into our calculator that the sine of 0.75, the sine inverse of 0.75 produced 0.48. So in order to find the quadrant 2, we're just going to go all the way around to pi, and then we're going to back out that reference angle. Doing that is what's going to help us determine what that other angle measure is. Continuing to solve by dividing both sides of each equation by 0.628, the solution of both x equals 1.35 or 3.65 from the graph are now explained. So we now know where this 1.35 is coming from. We now know where this 3.65 is coming from. But what about the rest of the answers? Well, from our work with periodic functions, we know that they repeat regularly. In this case, the period of the function is 2 pi. Let me write this down. The period of this function is equal to 2 pi divided by that b value of 0.628, which is approximately 10. Therefore, approximately every 10 years, the values that we see are going to repeat. So if we add 10, approximately 10, repeatedly to the solutions of 1.35, so I'm going to add 10, and also to 3.65, I'm going to add 10. If I do that repeatedly, then the other solutions can be found. Since there are technically infinite solutions, it's really impossible for us to write them all down, so we need a shorthand way of doing that. So this is what we're going to say. We're going to say that the solution for x is approximately the 1.35 plus that period, which was 10, times multiples of k, where k, what the heck is k? K is an integer, and that fancy looking z right there, that's fancy notation for saying that k is an element of the integers. Here's what we mean by that. Integers are all the whole numbers, so 0, 1, 2, 3, 4, 5, and their opposites. So just imagine here if we let k equal 1. What we're basically talking about is just taking 1.35 plus 10. If we let k equal 2, now we're saying we're going to add another period to it. Now, taking k values that are positive is going to give us all the positive values to the right. If we want to go to the left, then that's where we see k values that are negative, and that's what would take us the opposite direction if that was something that we wanted. Now, I have to not only write this for the 1.35, but I also need to write it for the other solution, which is 3.65 plus 10k, where again we say that k is an element of the integers.